Your audio is, I guess,
should be working.
Okay, our speaker today is Chris Riseley. Chris is here since 2019 as a postdoc in Bonafide's group. He got his PhD working under the supervision of Anna Scaif in Southampton and in Manchester. Then he moved to Australia and he worked as a postdoc under the supervision of George Hill. And then he moved here. Meanwhile, he became very experienced in using most of the radio telescope available. He's currently co-chair of the cluster working group connected with the EMU possum survey with ASCAP, and is also the leading scientist, the project scientist of NWA. And today he'll tell us the latest wonders about some class of diffuse radio emission in cluster galaxies.
Cool. Thank you, Franco. Thanks everyone for being here. Hopefully, if I project my voice loud enough, people will be able to hear online. I'll be using my laser pointer, which you won't see online, but I'll try and describe where it's pointing for convenience. So I'm going to talk to you today about halos and mini halos in clusters of galaxies. In particular, this is a topic that has been occupying my attention a lot for the last few years. So I'm going to be talking about what we know about mini halos, what we're finding out, and all the kind of interesting science we're doing with the next generation of radio telescopes.
Sorry to stop you.
Yes.
If you use the background in the video, they saw you without your head. So you speak.
Okay.
It's funny, but so maybe either remove the background or you look like.
Okay. Okay. Give me a minute.
Or just switch the camera on. Yeah,
there we go.
That's perfect.
No virtual background. Otherwise, yeah, be occasionally a ghost floating in and out. Otherwise, they just see that background that's on the left. I'm gonna have to click on here. So first things first, a little bit of background. I always like to, I've got a few slides on this so that I like to get everyone on the same page. So galaxy clusters 101. When we're talking about galaxy clusters, we're talking about these structures, the largest gravitationally bound objects in the universe that form at the nodes and intersections of the cosmic web. The overall mass budget is dominated by dark matter, which we trace by things like lensing, and you can use the SZ effect. When we zoom in on these nodes and intersections, in clusters of galaxies, in terms of actual galaxies, we've got hundreds to thousands in clusters. These only represent a few percent of the total mass budget. Then you see the intracluster medium, or ICM. This is your hot plasma soup that fills the vast majority of the volume of a galaxy cluster. Very, very rarefied, very hot plasma. And in this talk, and in many works that you will see about galaxy clusters, you hear the ICM referred to as the thermal component or thermal components. And this is about 15% of the total budget. And then we have diffuse synchrotron emission, and now you can see which cluster this is. This traces the relativistic electrons and magnetic fields on the largest scales in the universe. And in this talk and other galaxy cluster talks and papers, you'll hear the synchrotron emission referred to as the non-thermal components. And of course, just in case anyone's not familiar with this object, this is Abell 2744 that has been studied for several decades now in the radio and X-ray regimes, as well as others. Clusters host a lot of different weird and wonderful sources, such as radio galaxies, which are relatively run-of-the-mill, although in clusters they exhibit a wide variety of shapes and sizes. You've got radio halos, and you've got radio relics sitting here at the cluster periphery. These are just two of the relics in Abell 2744, which actually hosts, I think, up to 4 relics, but these are just the 2 that are most clearly visible. So clusters are rich environments for a rich variety of physics. Now, Galaxy Clusters 102, my second introduction slide. This is probably, and this doesn't actually project amazingly well, so feel free to watch the recording, or if you're seeing online, this is one of my preferred ways to visualize clusters, because when we overlay this multi-wavelength data, we see the radio emission in your warm colors, your yellows, oranges, and reds, and then you see your hot plasma in blue colors. So multi-wavelength studies are a way to get to the underlying physics of what's going on, because looking with any, these sources, typically all synchrotron sources in clusters have a spectrum that to first order looks something a little bit like this. There's a few caveats to this. but broadly speaking, you've got your power law, and then at higher frequencies, you've got some exponential break, and as the source ages, that moves to lower and lower frequencies. And so to get to the underlying physics, we need access to this data. We're talking about getting at the energetics to understand what's going on in clusters. To get to the energetics, we need to look at the spectrum, which necessitates this multi-wavelength approach. And aside from making pretty pictures, this multi-wavelength approach gives us access to the underlying physics, which is the big question we're trying to answer with these kind of studies is what powers diffuse radio emission on the largest scales? This brings us onto the non-thermal zoo. Strictly speaking, theoretically, we have 3 distinct classes of sources dating back of the order of 2 decades, such as radio halos and radio relics. And here's a couple of examples from COMA. And then on the much smaller scale, you have mini halos. Now, with halos and relics, there have been sort of the order of 100 clusters hosting some combination of relics and or halos. But mini halos are much more enigmatic, much less well explored, and there's of the order of 40 that will be studied hosting mini halos. It's pretty commonly accepted that halos are powered by some form of MHD turbulence following cluster mergers. Radio relics are broadly speaking, driven by shocks, so some form of diffusive shock, acceleration or reacceleration. And mini halos, the jury's still out. This is one of the questions that we're trying to answer. There are some studies that have previously suggested turbulence. There are some studies that have suggested hadronics. Don't worry if you're not familiar with these terms. These are something I'm going to come on to explain in a little bit. Or more recently, and this is the evolving picture of where the research is going, perhaps some form of hybrid scenario where you have turbulence and hadronics dominant on different scales. Onto mini halos. These are relatively small. We're still talking hundreds of kiloparsec scales, diffuse radio sources that are tracing in situ acceleration or reacceleration, hosted by relaxed cool core clusters. One of the canonical examples is the mini halo in the Perseus cluster. Broadly speaking, as I mentioned, we have 2 different types of injection scenario. You've either got hadronics, where you've got secondary electrons that are generated by the collision of high energy protons and thermal protons, which via a cascade of particles produce secondary relativistic electrons. And where do we get cosmic ray protons in clusters of galaxies? A variety of sources, including AGN. They're present and ubiquitous in the universe and in clusters of galaxies, and so they will seed these cosmic ray protons to some level throughout the intracluster medium. Alternatively, turbulence. Turbulence is a well-tunable and ubiquitous process in clusters of galaxies. In Perseus's cluster that is known to have turbulence produced by core sloshing. You can think of this in a real-world example as the sloshing of wine in a glass, but when you look at the structure of the core in Perseus, it's sloshing much more like this. So now, when it comes to mini halos in particular, the big question is the balance between these mechanisms, because we know they will both be present on some scales, but what's the balance? What's the scales? One of the textbook examples of mini halos is RxJ 1720, which in an older paper from Simona Giacintucci and collaborators, they found this mini halo, which was sort of a couple of hundred kiloparsecs in size. When you get new data at lower frequencies, it's actually much larger. I've scaled these so they roughly trace the same physical scale, and so you can see all of this diffuse emission is contained within this region, and that extension up here is this radio galaxy. But there's all of this steep spectrum emission that you can only see with the latest data going to the lowest frequencies. And you can see very different spectral indexes in the different regions, which trace the age of the electrons and the efficiency of the mechanisms. And one of the things that we have, one of the tools we have at our disposal to understand the energetics and what's going on is looking at these point-to-point correlations between thermal and non-thermal. The strength of this correlation tells us about the strength of the connection between the 2 different components in the intercluster medium. The slope provides us insights into the acceleration mechanism and the relative distribution of thermal and non-thermal components. The structure tells us whether we may have different regions with different mechanisms or different microclimate. And the spectral dependence any change with frequency, that gives us additional information on the underlying acceleration mechanism. So you're going to see a few of these point-to-point correlations in this talk, and these are the key things to try and bear in mind. We're interested in the strength, the slope, structure, and the spectral dependence for S's. And so in RHA 1720, what Nadia and collaborators found was that the different regions have very strongly different correlations. One of the open questions was, is this tracing different acceleration processes or different microclimate? And this is where my big flagship project from the last few years comes in, the MeerKAT-meets-LOFAR mini halo census. We're trying to answer this question by using the two most sensitive radio interferometers in the world, MeerKAT and LOFAR. Going to low frequencies with LOFAR allows us to get access to older electrons, inefficient or weak acceleration processes. We use data from LOFAR surveys plus a few other sources. Higher frequencies with MeerKAT gives us access to fresher electron populations, and I was awarded 74 hours at priority A time a few years ago. And we supplement this with other data sets from like GMRT and VLA where possible, and we get there's MeerKAT in South Africa. And we supplement with Chandra and XMM where possible for the thermal window. So now this synergy gives us access to the spectrum, which gives us access to information on the underlying physical processes. However, these telescopes are, of course, on the other side, on opposite sides of the world from each other. So we have a relatively narrow window of intersection between roughly Dec -1 to Dec +30. And so we get a sample of 13 mini halos, which is a reasonable size sample and represents sort of more than a quarter of the known population, more than a third of the known population at the time. So this is a good statistically significant sample to work with. I'm going to talk to you today about 3 of the examples from this census, 2 of which have been published and 1 of which will soon be submitted. So these are older images from GMRT on optical and VLA on optical data from papers sort of 10 plus years ago versus the data we have now on these 3 clusters, MS 1455, Abel 1413, and the one I'm currently working on, Abel 2142. These are all spectacular, interesting systems. And as it happens, they kind of represent a continuum from more relaxed to more disturbed clusters. So the new insights from MS 1455, which we published last year, our new data shows us that actually this mini halo is roughly twice the size as it was previously theorized to be, sort of up to 600 kiloparsecs, which is much larger than the canonical size of mini halos. And previously, mini halos were thought to trace inefficient acceleration processes and thought to be a very steep spectrum. However, our new high-quality data is showing us that actually we're not looking at ultra-steep spectrum emission. We are talking about a spectral index of the order of -1, which is very typical for this kind of, for halos and relics and emerging mini halos. We looked at radial profiles along a couple of different directions, and they showed evidence of multiple components in different directions. So the cyan data points are tracing a wedge going along this kind of south direction, and you could probably figure this out just by looking at the map, but then when you look at the profiles, you can really see it. And the north wedge went kind of straight north where the contours are very closely packed together. And at both frequencies, we see similar behavior. We see multiple components towards the south, but not towards the north. From our reanalysis of X-ray data, we see this kind of large-scale core sloshing spiral. If you can think about, wine sloshing in a wine glass or the core sloshing in Perseus, we see this kind of same, what I refer to as like a flip 6 structure. This sort of inverted 6 shape is one of your classic smoking gun pieces of evidence for large-scale core sloshing. This means we're seeing turbulence at work in the intracluster medium. And in a number of clusters, X-ray observations have revealed sort of cold fronts, which are really believed to trace these sort of bulk motions of cold gas in the intracluster medium. Actually, our reanalysis of this same data using new techniques showed that these cold fronts don't necessarily trace separate structures in the ICM, but they trace edges of large-scale features. So this really demonstrates also that with new techniques, we can get new discoveries and new value out of older data. And then when you see where the radio emission lies, the brighter part of the mini halo fills and traces this inverted, this flip six, this sloshing spiral. But when we look at lower frequencies, lower resolution, sorry, this is all our MeerKAT data, the radio emission goes quite a long way beyond the sloshing spiral. So while we've got this clear evidence of turbulence at work in the intercluster medium, if the particle acceleration is combined to the region where we've got the strong signs of turbulence, how are we getting acceleration on these very large scales outside there? That's one of the questions that we were working on answering. Moving on briefly to Abel 1413. Again, from the non-thermal point of view, we're talking radio emission that is about 600 kiloparsecs in size. It's twice as large as it was previously thought to be. And it's also quite asymmetric. So this is, again, I'm showing MeerKAT on the left and LOFAR on the right, which, as an interesting addendum, even though we're firmly in the northern sky, which you might think of as LOFAR's territory, MeerKAT's sensitivity and dynamic range and imaging performance is still phenomenal, even a DEC plus 25 or thereabouts. So consider using MeerKAT in the northern sky, not just the southern sky, because it's a phenomenal telescope. The spectrum is similarly around -1. It's, again, not ultra steep, and it's largely homogeneous. But in contrast to MS-1455, we see tentative evidence of steepening in some of the outer regions. But again, unfortunately, it's LOFAR's imaging performance is quite low declarations for LOFAR that is letting us down a little bit. And again, it's harder to see, and we couldn't fit it very well, so I actually didn't put this in the paper. But we do see tentative evidence of multiple components because we're seeing there's additional surface brightness excesses at larger radii. On the thermal point of view, looking at ICM temperature maps here for MS-1455 and Abel 1413 here. There's no cool core in Abel 1413, which is unusual. It's in fact known as it's a warm core cluster. It is the only mini halo hosting cluster that does not have a cool core. But this probably tells us, and this lines up with the multi-wavelength evidence there's a bit of an asymmetric galaxy distribution in the north-south direction. This probably tells us that the contribution from turbulence is greater for Abel 1413 than MS-1455, which has this very, very clear cool core. Yeah. The summary of our work on Abel 1413, it's got a warm core, it's asymmetric, we see multiple components. This gives us clues that the contribution from turbulence is greater. And there's a really neat little bit of math that we did at the end of this paper to explore the kind of point-to-point correlation you would expect from reacceleration of secondary particles. So if you're interested in clusters and you're starting to look at point-to-point correlations, then please do check it out. Point-to-point correlations. This is just as a quick reminder, we're interested in studying the strength, the four S's, the strength, the slope, the structure, and the spectral dependence, frequency dependence. We did the point-to-point correlation at both frequencies, and essentially what this tells us, at both frequencies for both clusters, we have a superlinear slope, which tells us that the non-thermal distribution, our relativistic electrons and magnetic fields, are more peaked than the thermal distribution. For MS-1455, which you're seeing on the top, with MeerKAT and LOFAR, we see, roughly speaking, a single component, even when we're looking at regions that are inside and outside the sloshing spiral, which are traced by the different colors for those of you online. Pink regions are inside the sloshing spiral, where we expect the contribution of turbulence to be greater, and cyan data points are outside the sloshing spiral. We see a single behavior. We don't see any deviation, any clear deviation from a single component. And there's no sign of spectral steepening between 1.2 gigahertz and 145 megahertz, just in case you can't see the numbers from the projector. This is a frequency independent slope, which is somewhat unexpected, perhaps, but all this really tells us is that there's no clear evidence of spectral steepening. For Abel 14, though, we see a single behavior throughout the entire structure. However, we see a much steeper slope with MeerKAT at high frequencies than with LOFAR at low frequencies. And what this tells us is that we have spectral steepening going on. So even though we don't necessarily see it from some of the other probes, we have spectral steepening. And this is perhaps more in tune with the interpretation that we have greater contribution from turbulence. And so this kind of brings us to the point of where the field is going with this whole turbulence versus hadronic. We're kind of putting that scenario in the bin. And now we're looking at scenarios where we have contributions from turbulence plus hadronics, perhaps on different scales. And this is kind of where the field is moving and where there's a lot of interest from the theoretical side. As a brief addendum before going on to ABEL 2142, there's a real wide field bonanza with these fields, because here's just some examples of MS 1455. Just you see the cluster there in the center. But there's lots of interesting stuff in the wider field. You've got all kinds of bent-tailed radio galaxies where the host galaxy is here. This is not associated with any known cluster, but you don't get structures like that outside of overdense environments. We see giant radio galaxies, an average of 1 giant radio galaxy per field. Again, you've got the host here, and then the jet is very well collimated, and then suddenly deviates in that direction, and likewise slowly bends along this direction. And if giant radio galaxies are your thing, come and talk to me, because there's all of this data sitting there. I want people to. The entire purpose of this survey, well, one of the bonuses of the survey is to generate high-quality, wide-field data products that other people can do their ancillary science with. And if odd radio circles or AUKs are your bag, which are, then, you know, we have at least one AUK. Unfortunately, it's a known one in one of the fields. It's about 45 arc, it's about 30 arc minutes east or west of ABEL 2142. So all of this kind of stuff is being unlocked from this wide field bonanza. 2 minutes. Oh my.
No, 5 minutes.
5 minutes. Okay, great. Perfect. ABEL 2142 is the next cluster that I'm working on. It's very different. It's well, it's quite different. It's dynamically disturbed. It's a merging system. It's very interesting. The key points. MeerKAT recovers, once we subtract all of the radio sources apart from these two embedded radio galaxies, which were painful, but I actually have dealt with them. I just haven't updated this plot. And also this radio galaxy. MeerKAT recovers diffuse radio emission from the halo up to around 1.5 megaparsecs in size. But if you can see the faint red haze there, or we overlay the LOFAR contours, we see that within a region of around 1 megaparsec radius centered on the cluster center, that's what this dashed circle is, roughly, we see a 2 megaparsec roughly region full of synchrotron emission. So even though this is not a major merging system, this cluster is just full of diffuse synchrotron emission. It's super rich and super interesting to study. It's fairly steep spectrum throughout, though again, I emphasize, not ultra steep spectrum. We see a spectral index of around minus 1.15, which again is very typical of radio halos and radio relics. And the color is really not coming out very well there. So if you want to see it, come talk to me later. But from the thermal point of view, this is a very interesting cluster because it's a merging system, dynamically disturbed, with, I believe, 4 sets of cold fronts, which one of the interpretations is that this is tracing the remnants of a cool core cluster that has undergone a significant merger sometime in the past. And the cool core has been not completely disrupted, but disrupted enough to be somewhat torn apart and spread out. And is perhaps given as given as an example of extreme core sloshing. So we know there's significant turbulence in this system. We looked at profiles along a variety of different directions, excluding this wedge, as this is where significant residuals remain from the subtraction of those sources. And what we see along these different arcs are profiles that look like this. You're seeing MeerKAT on the top and LOFAR on the bottom. The classical profile that we would fit is the e-folding exponential, and we attempted to fit either 1 or 2 or even 3 components. 3 components didn't fit very well, and so we threw those models in the bin and stuck with 1 or 2 components. Along the southeastern arc, which is in the main direction of I believe, the merger and the main extension of the intercluster medium, looking at the radio maps, we would see 2 components. In the radial profiles, however, we don't see any strong evidence of two components. We just see a single smooth exponential fit with a very consistent e-folding radius. To the southwest, we don't see any evidence of a second component with MeerKAT. It's just consistent with a single component. But we do see a double component fit with LOFAR at lower frequencies. And you really can't see the second component on the projector, but it goes along around like that. Again, with the first component, they show very similar e-folding radii. And then finally, along the northeastern direction here with both MeerKAT and LOFAR, we do see evidence of two components, with the first one of which has a nicely consistent e-folding radius, and the second one is significantly larger with LOFAR, which really traces LOFAR's excellent sensitivity here. And the fact that LOFAR sees a lot more emission than MeerKAT, and this is the only one in my sample so far where this is the case, is really telling us this is probably steep spectrum emission. We would need to go a lot deeper with MeerKAT to recover it. And I would like to do that in the future if the Sorau TAC are nice to me. So Able 2142 is a super rich system. Stay tuned. I've got a paper draft in an advanced state, but there's a lot of interesting stuff here. So we definitely have two components along the northeast. We have two components emerging along the southwest. So in this kind of axis, we're definitely seeing two components. And along this axis, tentative evidence of a second component when we go to higher resolution, but we really can't say anything concrete about it. In the point-to-point correlation, what do we see? Well, when you look at it, first off, you see a superlinear slope with MeerKAT, but a sublinear slope with LOFAR. This is extremely unusual. And so one of the things, bearing in mind the earlier discussion about MeerKAT sensitivity here in the steep spectrum, if we use a matched region set, which is what you're seeing here, we have a sublinear slope for both MeerKAT and LOFAR, which is very much in tune with what we'd expect from turbulence. But again, this really shows that we need deeper, higher frequency data. The interpretation physically of a sublinear slope is that thermal distribution is more peaked than the non-thermal distribution, and this is a clear piece of evidence within the turbulent acceleration scenario. But it gets more complex because this is a multi-component halo, so we have the sensitivity and resolution to look at different sub-regions. And so what I've done, those colors are projecting okay. In the inner region, H1, the core, H2 is this extended component here, the ridge, and H3, just this outer region. We divide it up into different regions and we look at the point-to-point correlation in those different regions. And this is a complex plot that probably doesn't project super well. Every single one of the regions has a sublinear slope, and every single one of the regions is steeper at high frequencies, which tells us that we have spectral steepening. H1, the core, and H3, have the larger scale component, have a very similar slope. And perhaps this tells us about the underlying physical processes or the microclimate, or perhaps this tells us that H3 fills a lot of the volume of the cluster and underlies a lot of H1. H2, conversely, has a much flatter slope. Again, this is very much consistent with turbulence, but one of the things that we're investigating, because we have the sensitivity and resolution and data to do it, is looking at studying whether there is a correlation between the radiospectral index and the temperature. Because you might think that where you have more turbulence in the cluster, you might get more energy deposited into the ICM, and you might have a hotter temperature, and you might therefore expect more particle acceleration and a flatter spectrum. That's a lot of, there's a lot of assumptions built into that, and this was first reported some time ago and taken as a key piece of evidence for confirming turbulent acceleration, but new studies have shared some doubt on this, and this is very much a question where the jury is out. And so H2, the ridge, we don't see any correlation there. For H1, we see actually a moderate anti-correlation, i.e. hotter regions of the cluster seem to have a steeper spectrum, which is unexpected, perhaps to first order. And the physical interpretation of that is something we're still very much working on. And so I'm trying to find some time to sit down with Gianfranco and work through this. So this is very much evolving, and stay tuned. So to my conclusions, clusters are super cool, enigmatic objects, highly dynamic environments. There's not really any such thing as a relaxed cluster, because even those that don't look like they're undergoing a merger have turbulence. And so we can use them to study a wide range of physical processes. The multi-wavelength approach is absolutely essential. You can't do this without radio and X-ray. Optical is extremely handy, and SZ is also very useful because, you know, we're going to be waiting a little while for the new generation of X-ray telescopes, unfortunately. We've learned a lot from this, even just from these first 3 studies, about particle acceleration mechanisms, magnetic fields, the connection between the hot plasma and the synchrotron emission, and about galaxy evolution in dynamic environments. You can see, just looking at the colors of these sources, tracing yellow through to red, going from active injection to very steep spectrum emission. But these new insights, they bring a lot of new questions and a lot of new challenges, and really emphasize the connection between observation and theory. Theory needs to catch up with observation. Frankly, we've got some exquisite instrumentation. You can look at these papers for more on any of these systems. And to answer my questions that I posed in the title, do we know things? Yes, we have found out, but this is raising a lot of other questions. And so thank you for listening, and I'll take questions.
Thanks. So let's first start with some question by PhD. Go for it. Not too many at once, but let's. Yes.
Sorry, I was wondering that how do you define the border of those structures? So how do you define it? Is it based on the background of some signals or the background of the results?
Exactly. It's based on, so for just in case you can't hear online, the question was essentially, how do we define the borders of the structures? Yeah, excellent question. Like it's a basic thing, but it's super important to get right. You've got to basically go by your signal to noise. So typically, in the radio, we would typically define the edge based on either the 2 sigma or 3 sigma level. In some of these maps, you can see the emission kind of gets a bit patchy, where the signal to noise is low, and you start getting sort of your biases, Eddington bias, where you have sort of real emission on top of a noise fluctuation gets boosted above or below your chosen sigma level. And so it's difficult. It's somewhat subjective, somewhat objective, but you would go based on your sigma level. Typically for the point-to-point correlations, we use contiguous emission above 2 sigma. But generally, for defining the extent, most people would probably take 3 sigma as the minimum level.
Okay. I ask this because of the fact that I'm not an expert in radio, but if you have all those small substructures with the clusters and everything, do we need to subtract? Do we need to detect them and then subtract them from all the data that we have from those clusters? Are those essential for the next service? I guess that's why I asked that. How do you find those regions in there?
Yeah. So when it comes, this is something, actually, thank you for bringing this up, because I didn't really mention this. If you're a radio person, you could probably figure this out, but for the context of everyone else, when I'm doing all of this analysis, I'm trying to subtract all or as much of the flux from any radio galaxies as possible, for example. And so we would do the same kind of thing with the X-ray data. We would ideally work on point source subtracted observations. Of course, if there are regions where the subtraction is not as good as you would like, let's say, or where you can't subtract sources, then you just play it safe and exclude those.
Yep. It's like a follow-up question about that. When you are saying that you found that the 2 radius were larger, right? The size of these mini halos, that's because you have like better sensitivity, or is because you are going lower frequency?
It is little from column A, little from column B.
Okay.
So the previous data that I was referring to on these clusters typically the GMRT data is 600 megahertz. The VLA data that was on ABEL 1413 is 1.4 gigahertz. These are based on older data sets from narrowband instruments. And so with the techniques available at the time and the data quality at the time, you don't have the UV coverage to really capture and model and recover all of the highly extended radio emission, particularly for ABEL 2142, which is quite large on the sky. And in some of these older data sets, you also suffer from dynamic range problems, particularly with MS 1455 and to some extent ABEL 1413, because one of the typical things with mini halos is you have a brightest cluster galaxy sitting in the middle of a potential well, and then that's sort of surrounded by the diffuse emission of the mini halo. Very often, the brightest cluster galaxy is let's say powerful radio galaxy, powerful enough to be detected and have significant radio emission. And so where you have limited data quality, limited dynamic range, techniques of 15, 20 years ago, your calibration still has residual errors. And so that can bias your study. That biases how well you can recover the diffuse radio emission. So yes, it is partly that we have access to the new generation of low frequency telescopes, things like LOFAR and the MWA, although MWA, other side of the world, lower resolution than LOFAR. We're recovering diffuse radio emission on larger scales because these telescopes are low frequency. They trace the low energy electrons. These are older electrons and or electrons that are being accelerated weakly or with low efficiency. So there's partly that. It is partly also just that LOFAR and definitely MeerKAT are phenomenal telescopes. When you've got a lot of antennas, big bandwidths, excellent receivers, excellent technology, and fantastic techniques, you can do things these days that people only dreamed of 20 years ago. So the data quality, it's night and day in terms of the difference.
Very nice.
More questions, even
We have one over here.
Sorry? Sorry.
But the second cluster.
Yes, ABEL 1413.
Yes, that you said it is the only one in which we find a mini halo, but it does not have a full.
Yes.
But you basically found out that the mini halo is due to turbulence in that, right? So, and you also said that that's also maybe in the cause of the core. So why do you think there isn't more examples of mini halo?
That's a very insightful question. Thank you. For those watching along online, the question was related to ABEL 1413. I'm genuinely not sure how much you can hear online and whether they can hear questions or not. So
It should work, but
okay.
That's what it was.
Just for the sake of being clear, the question was related to ABEL 1413 and essentially kind of boiled down to, we see a mini halo in ABEL 1413. Why do we not see more mini halos in, let's say, warm core clusters? So the emerging picture is that really this distinction between mini halos and halos is very arbitrary, and it was based on the data that was available back in the day. 20, 30 years ago, when we were coming up with the classifications for these sources, people saw very large things and they called them halos, and they saw smaller things. Other people saw smaller things and called them mini halos. With the data that we have now, it's much less two distinct categories and more of a continuum. And so if we're going to stick with, for the sake of argument, the mini halo paradigm, mini halos, you need to inject enough if they're driven by turbulence, you need to inject enough turbulence into the cluster to cause particle acceleration and generate the mini halo. without causing enough large-scale disruption of the cluster that the ICM spreads out, and we get things that are more like halos. The question is, how do we do that? The answer is probably related to minor mergers, off-axis interactions, things like that, where you have two clusters that pass by and just kind of clip each other, or have very low mass mergers or accretion of groups onto clusters. Essentially, I think it boils down to the chances of such an event happening. Of course, part of this also relates to the quality of the available X-ray data which we have to study these clusters. To detect a cool core or not, we need good quality X-ray data where we can get we have sufficient signal to noise to look at the ICM, and these are all, most of the mini halo hosting clusters are relatively small in spatial extent. You don't have that many clusters like Perseus and Fucus, where they're, well, I don't remember what redshift Fucus is, but Perseus, where you have a nearby enough cluster where you can see the ICM in a good spatial resolution with a low resolution telescope. So a lot of these clusters, you need things like, ideally Chandra. XMM can still do it to a good extent for some of these clusters, but really you need the high resolution instruments like Chandra.
Okay, can you elaborate a little bit more about the information we can extract from the point-to-point correlation? Because to me, it seems a very messy business. Everything depends on a lot of things, so not sure what is the basis.
Okay, I will have a go at elaborating. It might be a question better served for an extensive discussion with someone like Gianfranco, because
I don't want to do that.
Yeah, I can understand that. So historically, one of the clear predictions of, historically, one of the clear discriminators between turbulence and hadronics was the point-to-point correlation, because with a default set of parameters, the turbulent acceleration model will predict a sublinear slope or maybe up to a linear slope, whereas a superlinear slope was only really reproduced under a hadronic scenario. However, turbulence is very, very tunable and has a lot of knobs and buttons and dials and things that you can tweak all of the parameters. And so one of the things that we looked at in the paper on Abel 1413, we did a very quick back of the envelope calculation to see what kind of slope you would predict from reacceleration of secondary electrons by turbulence. And in that scenario, you can also recreate a superlinear slope. So in terms of discriminating between the models, it's a piece of the puzzle. It's not necessarily a smoking gun piece of evidence. Although, if you have a sublinear slope, that pretty much instantly rules out a scenario where the halo or mini halo is generated just by secondary electrons from hadronics. But I don't think there are many people who truly believe that there are any mini halos, and certainly not any halos that are generated purely by hadronics. Because we see, these are hot turbulent environments, we see turbulence everywhere. So even though we get secondary electrons from hadronic collisions, turbulence plays a role that we can't ignore. One of the things that I'm particularly interested in looking at is doing this spatially, like we did here for Abel 2142, looking at different regions of halos and seeing whether these regions follow different trends. Because that can tell us things about potentially different physical conditions. It might be able to allow us to infer things about the geometry of the system. And looking for multiple component, it's also another way of seeing whether we have multiple component emission. If we can't see evidence of different components in radial profiles, let's say, we can also use the point-to-point correlation.
These conclusions are sensitive to the radial profile of magnetic field, for example.
Yes.
That can change.
Yeah. It's one piece of the puzzle. It's a very powerful probe, but it doesn't, as with many of these techniques, it doesn't give us everything.
Is there time for 2 questions?
Right.
Very quick. The first one is about the first cluster you showed. So there, when you go to deeper sensitivity and lower frequency, but in any case, you see much more extended emission than previously thought, right? And you mentioned that extends outside the sloshing region. Am I correct? Okay.
Yes. I can. Yeah. Anyway, carry on.
Yeah, this one. But if you define the sloshing region as the region where you see cold fronts, that also depends on the sensitivity of the X-ray observation.
Yes.
So maybe that you actually have outer cold fronts out there that match the extent, because there have been papers that mention like megaparsec scale cold fronts.
Exactly.
Is it possible?
It's absolutely possible. Yes. You can see. I don't know whether you can see from where you're sitting, but in this figure, you can kind of see the limits, the outer limits of the X-ray data. So yes, absolutely. I would love there to be some, a couple of other 2 more Chandra telescopes out there in space that we could get a lot of time on all of these clusters with. The resolution here of the radio data is about 20 arc seconds. So a lot of these, it's touch and go whether you might be able to use something like, let's say, eRosita. XMM would probably be pretty good, and we have XMM data on a lot of these systems, but really Chandra and Chandra's arc second resolution capabilities are the most powerful thing.
Because you have to subtract one source.
Exactly.
The second question was on the spectral index to temperature relation.
Oh, yes.
So you said that it's really weird that other regions have flatter spectral index.
No, we see the contrary. Okay. We see.
So when you say hotter or colder, anyway, what's the reference? Because you mean underneath, if you have a structured cluster like a full core or even a weak full core cluster, you have a gradient there. So what if you weighted the temperature by the average at the radius, maybe? So you could say that it is actually colder with respect to the average there, because it will never be colder than a region that is closer to the center, right?
It's a good point. I only put this plot together the other day, but this is something that looking at correlations between spectral index and X-ray temperature is something that this is the first time I think I've done it in my career so far. It's something that not a lot of people have the data quality to do. So that's a really interesting idea, and it would be good to check out whether that has an impact or not. In terms of this specific example, H1 and H2 are both quite close to the well, H1 is basically tracing the core of the cluster, and H2 is slightly away from the core of the cluster, but they're not particularly far away from the center, the pointing center of Chandra for these. Maybe this is something that Andrea or Luca might be able to comment better on, whether this is how much power this might have. But we can talk about that offline, because I see Andrea's online right now. But yeah, let's talk about it afterwards, Andrea. Any other questions?
Okay.
Any questions online? Going once? Going twice?
No, I don't think so.
Okay.
Okay, then thanks again.